Hello YouTube viewers, welcome to my show Science Thursday. In today's episode we're gonna take a look at stepper motors. So why there is a need for something like this? You have to understand we are relying on computers more and more each day. So we need some way that our software or computers can interact with the physical world. So we need something known as computer control. Now you must have also heard normal things like this air condition is computer controlled, and this refrigerator is computer, this washing machine is computer. All they are meaning is that computer can affect the operation of the equipment. So this is something like that. Now we need precise motion. For this application, like hard drive, in your hard drive, that arm that is going back and forth, it is using a stepper motor, and without it, it cannot reliably read or write data on that magnetic platters. So for that reason, we have to have a precision controlled system. And also for printer, as you can see, like it rolls out, the paper comes out, and then you have a head that is going back and forth. So how much is going back and forth, that must be controlled, and computer also need a feedback, otherwise it does not know when to give off the ink. Like let's say there is a blue circle, so it has to be like off, print blue, off, print blue, then again, like that it has to keep doing it. For this reason we need precision, and we can achieve this by many other methods like servo methods. However, they are very expensive because of their closed loop design, because they need a feedback. They will send signal to the motor will rotate, and a feedback loop will check how much you have it rotated. So for that reason we needed something that is called open loop. Basically you just send the signal and you can be reasonably confident that your job was done. So this is a stepper motor. How does it work? Now I'm not gonna go in depth for it. You don't need to know. Like, all you need to know is that all the magnetic rotor, that things that rotate, is of permanent magnet, and it has spikes or teeth as it's called. So does the electromagnet that is on the stator. Now this creates a very unique magnetic arrangement, in which scenario you end up in a scenario where the teeth wants to align with itself. Now that alignment is the reason why the motor does not keep spinning independently. Because of the teeth nature, it's like it always wants to snap, and the count of the teeth is generally created such a way that any given moment of time it can only snap to one place. So like if this is stator coil is on, it will snap that way. If this is on, it will be off that way. Now the offset is the one that allows you to rotate it, because if you don't have the offset, all it will be like it will be permanently static. So there is an offset. Now that offset and coupled with that electronic control gives us what we call steps. So most of you are those who have worked with stepper motors, they will know like each degree of the motor is generally divided in steps, and you can find a motor that rotates 3 degree per step, 5 degree per step, or 0.5 degree per steps. Like that's how it is. So your computer knows if I send 5 step signal, it has rotated like let's say 12 degrees. So this is the core aspect of the stepper motor. That's why we call it stepper motor. It steps, and if you give it the signal, and it is capable of doing it, like you can't move a 5-ton car with this. So if it can handle the load, it will do the job. So that's why the open loop part is, and the construction of it is more or less like a brushless DC motor. And be mindful, you can't run it with a DC brushless motor drivers. It needs its own driver. That's a kind of complex aspect of it. And if you really want to go in depth, there are Wikipedia articles and YouTube links that you can find, which will do a very good job. I'm just giving a basic idea that there are teeth in the rotor and there are teeth in the stator, both align, and that alignment only can happen at one point, like this or this or this or this. That's how it controls how much it rotates. Now, what are the pros of this method? One very simple pro that I have put at the top is what's called holding torque. Now, what you have to understand about holding torque is, like, imagine you have a robotic arm that is going like this. You have a axle that is rotating like this, up and down. Now, in normal motors, the servo motors, you see, you can do up and down. However, you cannot go like this and stop. it does not have hold it now, it will go back down again. So the way in servo system we use that is either we have a gear system that blocks, you know, backwards rotation or things like that, or generally we apply brakes there. So the moment encoder tells, yeah, you reach this point, it will apply a physical brake. However, for stepper motors, you don't need to do that. Because of that teeth arrangement, it can lock onto it. So basically, if it's rotating and, like, let's say it has an arm that is heavy and it's like, you know, it has to spend energy to move it up, it can actually hold it. It's like, okay, I'm gonna hold it. So this is very crucial for many robotic application, as you can see. So many times they are lifting a car and truck. Of course, they will also apply brakes, because holding torque is not free. You have to spend electricity on it. So they will do it, and if it's like small instant, like, you know, only for 1 second they have to do like this, they wouldn't bother with brakes. But if, like, let's say this robot has to lift that car and be like this for 5 minutes until that another robot does, then they will apply brakes. But this does have holding torque. Now, I said this is open loop system. What does that mean? It does not need an encoder. It's an open system. It does not require another circuitry going back and forth that is telling whether has it rotated or not, has it rotated this much or not. You can add those things, but it can work without it. There is no feedback in your printer or 3D printer or most CNC also, like low level CNC. High level does have feedbacks, and it's very simple. Because there is no brushes going around connecting anything, it's quite reliable and it can go on for decades. You can keep replacing the electronics and the motor will keep running. So those are the pro. How about the cons? It has no feedback mechanism for missed step. Let's say you told it, like, okay, rotate 2 times. Let's say it only rotated 1.7 times. There is no way in the inherent design of the motor that the driver unit will know, oh, my motor has missed, I have to overdrive it, so compensate. There is no feedback internally. You can do it externally, but then again, you end up with a place where you have to add a encoder, rotary circuits and things like that. So this is very crucial. This is why when you have very high precision operation like medical robots or robots that are doing the welding for aircraft or things like that, they always have a feedback system, because it cannot tell you whether you have missed a step or not. Second, it has low torque at high speed. This is the very weird aspect of this motor, very specifically, because almost all motors have near linear torque, like not absolutely linear, but you get the idea. It's more or less the same. At 10 rpm it has the same torque, at 50 rpm it has the same. However, this is very crucial with stepper motors. They lose torque if you rotate them very fast. So let's say you have a CNC bed that is very long, and motor has to go along, it has to go very slowly, otherwise it will simply lose its step, and it has to overdrive, otherwise because there is a lack of torque. So if you are doing a CNC bit that is going on a wood and it's carving it, it's a low torque, no issue. But you do it with steel, it needs to know whether it's slipping or not, and if you do it very fast, the motor simply does not have the torque, and it requires very complex driver. Now this is a graph of what we call driving arrangements. So as you can see, this is first is wave drive. We no longer use that. This is full step. So if you buy a controller for your stepper motor, they will simply tell you how much resolution it allows you to, like, can it do full step, can it do half step, can it do micro stepping. Now each of this method has its own advantage. Like for some application where torque is of the utmost importance, you're gonna use full wave, and some places where you don't want a silent operation, let's say you're doing a laser cutter which does not have any torque application to it, like it does not resist. Laser has no resistance, like a CNC milling bit has a resistance, like there is a resistance going on. You might want to use micro streaming. That will also increase your resolution. So it's not that you can use one with everything, but you have to pick and choose. And as you can see, this is what happens when a 3D printer misses its steps. As you can see, like, it's printing the correct thing, is just offset. That offset happened because there is no feedback. So stepper motors are quite important. As I already told you, it's in your hard drive, in your printer, in your CD drive, everywhere. So what's next? Now stepper motors have a lot of potential that is untapped simply because it does not have a feedback system, which we can compensate by applying an encoder pathway. Basically, you will have the motor and you'll have an encoder on the back. Now that encoder will allow you to do simple things like, oh, my motor has missed few steps, I'm gonna overdrive it. Of course, software also needs to be written like this, so it can actually compensate for that. But this is one next step for stepper motors. You can still buy these, They are kind of expensive, but if you are building a CNC machine that has to work with tough materials like high grade aluminum or very strong steel, you need these sort of things. And advanced stepper motor controller, as I already showed you, there is a graph, and currently we don't have the technology where to make them at cheap. They are quite expensive. You can buy a microcontroller that does everything, however it will be very expensive. So these two are the next evolution of stepper motors. First, the encoder will become more widely spread, so even normal 3D printers will start having them. And of course, with advanced stepper motor controller, you will also have a noisy, very low noise stepper motor. Without it, its motors are quite noisy. Now that noise comes because of the motions that's happening, and to control that you have to send the signal. For, as you can see, they're already so complicated because it has to know the position and everything. We expect to see very advanced computer control circuitry on motor itself. This was my presentation on stepper motor, a brief summary. I hope you liked it, and if you did, please like. If you didn't, dislike. Leave a comment on what you want to see in next episode of Science Thursday, and as always, subscribe and press the bell icon. I make video every day, and as always, thanks for watching.